So, welcome back to one more presentation on data movements. We have already seen a little introduction in our previous presentation itself. After having seen the shift register operations, right? We have moved to the data handling, instructions, wherein we need to deal with the registers as we have seen, right? So far, whatever the operation we were doing, they were all with respect to the bits, but once when you want to handle numbers, could it be the temperature or any analog value that is being sensed by your sensors, right? So then we need to deal with the registers. So whenever we have to deal with the registers, as I have already given you some of the examples in the previous presentation, right? We need to deal with some of the data handling instructions. So out of which the first one happens to be the data movement, right? So as you can see here, this is from source to destination in your microcontroller or your microprocessor, whatever you have said earlier, right? In all these cases, probably you know how exactly the simple data handling instructions happen, right? So for example, this may be a very common instruction which you have come across in your microprocessor or microcontroller: move a comma b, right? So this is the operation, these are the operands, right? So whenever I say move a comma b, the content of b is made to move to content of a, where your b is the destination and a is the source. So this is a simple reminder for you to come across how exactly we will have the similar instructions as long as the PLC scenario is concerned. So now let me take up this kind of the data movement instructions format as long as my Mitsubishi PLC is concerned. So it looks something like this. You can see here, this is the switch which is required in almost all the operation, because the PLC operations are basically meant by means the input and output devices. And if you take it something like this, this completes one rung of a ladder diagram as long as the data movement instruction is concerned. So what I will write here as move, you can see here, I will make it small, right? So then we have the source here, then you have the destination here. This is how the things look like as long as the data handling is concerned. Yeah. And again, needless to mention that this is the switch which is responsible for the data movement operation, right? So here I have this as D1, this as D2, right? So this is the source address, and this is the destination address. So whenever this switch is closed, or whenever you get an instruction or whenever you get an action for you to close this switch, maybe a photo sensor, whatever it is, right? So as long as the subsequent part of this rung is this one, right, you will have move the content of source into the destination, and maybe so you know where exactly the source data is stored, where exactly the destination data is stored, which should be already should have been defined earlier, and accordingly you have the various configurations for that, which we are not interested for the time being. Whenever I use this instruction, my data gets transferred from the source to destination, right? This is one syntax which you can see as long as the data movement instruction is concerned, what we have seen here, source to destination. And here the different the PLCs make use of the different types of notations. So since I am using the Mitsubishi configuration as per our curriculum, I have taken this particular ladder rung, which represents a data movement instruction as long as a Mitsubishi configuration is concerned, right? So then the next one happens to be a very important one, data comparison. This is also one of the very common type of action that is required to be carried out in your industrial process control and all, right? So now, for example, when the temperature reaches some preset value, right, so you have to take some action. When the pressure goes below some value, right, so you have to take some action. Like that, whenever some action is necessary to be taken, so some kind of comparison is to be done. And in order to do that kind of comparison, as long as you are comparing some analog values, so long as it is not a bit, okay, the comparison of the bit will be very easy, right? Whereas when you go into the comparison of the bytes or the nibbles, then you will have to go with the data comparison instructions, right? So now we have already taken some examples in our instruction list, right, if you remember correctly, right? So now check the pressure, whether the pressure P1, for example, is less than P2, right? Then you have seen the if else type of statements in your structure text, right? If P1 is less than P2, then switch A, something like this, right? Else switch B, something like this. So these kind of operations we have seen. So in order to have these kind of operations, right, we have the different types of the nomenclatures here, right? So these nomenclatures basically take us to the different types of comparison. So the first one is less than, okay, so this is the keyword, right? So generally these are taken like this, or it is taken like this in different notations, right? Some cases it is taken like this, these mnemonic type of operations, right? So we can see, so Mitsubishi makes use of this kind of notations, right? Whereas your Siemens or Allen Bradley, they have their own configuration. As I've already told you in the beginning itself, let us confine our discussion to only one type of notation so that there will not be any confusions, right? So this is as long as the less than is concerned. Then you have got something called as greater than, again like this, or GT in some cases, right? Or in some cases it is GT, GRT in some cases, something like this, okay? So or sometimes you have equal, if A equal to B or equal to, in some cases you have just one equality symbol, in some cases you have this kind of symbol, you know what is the difference between these two, right? One is checking, the second one is the assignment, or in some cases you might have something like this EQ, or in some cases you have EQ U also, right? So these are some of the representations, right? And you may have even not equal to, this also you may have, right? So whenever you have not equal to, you will have this representation. In some cases you have this kind of representation, or in some cases you have only NE, or in some cases you have NEQ, something like this, right? So these are some of the commonly used, representations as long as the data comparison is concerned. So this sometimes you may have less than or equal to, right? So, or sometimes you may have greater than or equal to also. So that all depends upon what kind of situation you come across. So you know, generally for less than or equal to you use this, greater than or equal to you use this. So that all depends upon where exactly you use them. Now what is important for us is how exactly you will write these things as long as the Mitsubishi configuration is concerned, right? So now if I start drawing the rung of a ladder here, so look something like this. So you have again as usual a switch which takes care of initiating this operation, the comparison operation. Then as it is, you would have three parts here, 1 2 3. Then should lead to, you know, some kind of the output action. So now if I say this is X 400, something like this, right? So now use this symbol, right? This as S, this as D, this as Y 430 or something like this. So now this particular diagram or the rung of the ladder is easily understandable to you, because when you have, see, actuated one input X400, right? So then your comparison task should begin as long as your source data is greater than the destination data. You will have to activate the output Y430. So this is what is the meaning of this particular program or the rung, right, wherein you may have the advanced operation based on this particular basic operation. So now what exactly it shows is, so you initiate one operation, the comparison operation X400, as long as the source data is greater than the destination data, then you have the output activated, right? So now the same principle or the same example can be even expanded to one particular situation, wherein so you have some temp sensor. Let us say I have got one temperature sensor, okay, so which keeps measuring the temperature, right? So now as long as the temp say alarm, okay, so this should start sounding or ringing, right? So how long it should start sounding or ringing? Till your temperature goes below 90 degree centigrade. So if this is a kind of situation wherein you will have to draw a rung in the ladder diagram, so maybe by making use of say your timers and all, definitely these kind of things can be executed. But if you want to execute this type of operation, right, a temperature sensor being an input, then the temperature being the variable there, above 100 degree, below 90 degree, then your alarm being the output. In such cases, how would you draw the ladder diagram, right? So now you can see here, I just
source and destination are well defined earlier, right? So now I'm going to have one more representation here. This is my output, which otherwise in general I would have represented the output something like this, right? So now because it is a different operation, I am representing the output in slightly different manner. This is Y430 here. So now this is setting the output like this. You can see here now this is greater than. So this is K100. So somewhere I have got the setting as K, so which is your destination, and you have got the source, which may be the input from your temperature sensor, or could it be from thermocouple or thermometer, whatever it is, right? So which is a variable. So as long as your the destination value, right, or your source value becomes equal to the destination or more than that, right, you can have this also, right? So you are setting the output Y430, right? So now I need to have one more rung here, which is to take care of the other kind of operation which is required in my statement. This is resetting Y430. One is to set Y430, another is resetting 30. Now what I am doing is I am checking the other condition here, so as well as destination, right? And my setting here is 90. My setting here is 90, right? So now maybe here I need to use one more latch here, because this is Y430. You can understand why I have used the latch. As long as the temperature is above 100 degree, your output should keep giving the sound. That is the reason why I am using a latch circuit here, right? Once your output starts giving the signal, or the sound, something like that, it will keep on giving the sound as long as the temperature is above 100 degree, right? But it will even give you the sound as long as the temperature is between 90 to 100 degree. Above 100 degree means 90 to 100 degree also, right? So the temperature, this is the threshold 90 degree, and this is 100 degree. Now in this range also your output should keep giving the signal. But once the temperature is right, so the output should reset. That is taken care of by this particular part of your ladder program. So this is how you will be able to have the operation of a comparison of a physical data, right? May not be the bit here, right? As long as it is bit, you can easily realize it with the help of a timer or something like that. But as long as it is a byte or nibble or word of any width, so then you need to make use of the data handling instructions, out of which you are making use of the data comparison instruction. So this is one such example which could be useful for you. And now let me take up one more similar example, which probably you have seen even in the case of you know the timers and all, right? So now what should happen here is, let me take up this with the help of a timing diagram. That would be always better. I have got one switch, let me say that X400, something like this. I have got a switch here, right? And this switch will activate one output, something like this. So let me call this as Y430. This is easily understandable. Then you have got say a couple of other outputs, maybe Y431, something like this, then Y432, something like this, and you may have one more, let us say Y433, something like this, 432, Y433. These are the outputs. Now you know exactly where these outputs get activated. So now this is where your output pulse comes, right? So maybe your output Y430, even you can show it here also, not be any confusion, maybe something like this, and here I would slightly move it ahead so that, yeah, something like this we can take. Okay, so the moment your input pulse is appearing, or it goes down here, right? Or you can take a negligible width of this pulse, maybe a push button switch or something like that, whatever it is. So your output 30 gets activated. Now what you need to do is, you need to turn on one output after some times. So what is the gap here, that we can always take as per our requirement. This is an example here, right? So you have to turn on output after some more gap here, this one, right? And you have to turn on one more out after some more gap here, right? So these things you can definitely consider, maybe. So this is about 5 seconds. Okay, so now this may be say 10 seconds, this may be say 15 seconds, an example. Okay, so this is how you should have it, right? So here, by looking at this timing diagram, what you understand is, will activate one output instantaneously when one push button is pressed, right? So that is your Y430. And the second output, say it is Y431, is activated after some times. Say let us take that as about 10 seconds, and you activate one more output maybe after 15 seconds, then you activate one more output after 25 seconds of the occurrence of this X400. And we have also seen that this kind of operations can be easily realized with the help of your timers, right? But here also one timer is essential, because the basic delay whatever you are going to create here, right, you can always have with the help of the timer. But if you use 3 timers, then this program can be easily realized, as we have already taken this kind of examples earlier. But by making use of one timer and the data comparison instructions, right? So let us try to see how exactly we will be able to incorporate this operation in the ladder diagram, right? So the first part of the ladder diagram is quite simple, as you are very familiar with that. So I have one input here, which is X400. Then I activate one output also Y430. Then this will activate a timer. So now instead of this you can even have this connection here also, as we have seen. It could be like this also. You can have your own discretion to draw this. It doesn't make any difference as long as both the switches are same. You can have it coming in the second rung, or even you can take a parallel output. This kind of operations we have seen earlier, right? So now this is my timer. This is timer T450, something like this, right? And here I K for 25. K is set 25. So I will write it properly. K is set for 25. T450 and K is set for 25. So this is my X400. So this also is my X400, but this is irrelevant as long as I have this one. So if you want, I can remove this so that my one input X400 will take care of making Y430 on, and also a timer which is turning on, right? So now when I come to the next rung here I would use a data comparison block followed by that block which has got the output of Y431. And now this block, see here, this is greater than or equal to. Now here